Okay, so let's start on discussing the three different types of matter. So, just before we go into this, something I should say is that we will be discussing three types of matter. There are actually 6 different types of matter. However, we're not going to branch into that just now. All you will need to know are the main 3. So, the first one we'll discuss is a solid. So, a solid is something that has a defined shape and volume. So, with particles that cling rigidly to each other. So, that's what constitutes a solid. So, anything that's able to retain its shape. So, if you were to get a pen and you place your pen in a cup, your pen will not assume the shape of that cup. It will stay as the shape of a pen. So, therefore, it is a solid. Now, a liquid has a definite volume, but not a defined shape. So we have particles that will stick firmly, but not rigidly. So it means that essentially it will maintain its volume. If you have 1 liter of water, it doesn't matter whether you put it in a 1 liter container or a 10 liter container, you will still have 1 liter of water. However, it will not have a defined shape. So if you put it into a horse-shaped container, the water will look like a horse. And the last one is gas. Now, gas is quite interesting because it has an indefinite volume and no fixed shape. So essentially, these particles can then move independently of each other. They're not sticking to each other or dependent on each other, and they will try their best to occupy as much space as possible. We will be discussing gases a little bit further in the semester. And that's when we're going to learn about their characteristics and behavior. But the biggest things to take away are that what shape they will have depending on the scenario and the volume. So here we have water as an example. So water can exist in all 3 states. It can exist as a solid, a liquid, and a gas. So when it's in a solid form, what happens is that the water molecules will sort of attach themselves to each other. They'll want to sort of grip in, and that will form that rigid structure. That is why when you have an ice cube and you place it into your drink, it will still maintain the shape of when it was frozen. Next, if we were to sort of heat up our ice and turn it into liquid, what happens is, and remembering from our previous module, when we put energy into a system, so when we're heating this up, we're giving it energy. Now, when it has more energy, these molecules start to get restless. Picture, if you will, giving a small child a lot of sugar. They won't just want to sit still. They don't want to just be near other people. They want to move. They want to break away and run around and be as active and vigorous as possible. And that's literally what happens when we heat up our ice to a liquid. And because the water molecules start getting agitated, so if I draw water here, so we have H2O, which is water, and they want to stick to each other like this. So these hydrogens here will sort of want to be drawn to this oxygen here, and that's why it's a quite rigid structure. Now, as we heat them up, they start to get restless. They want to push each other away. And by doing that, these little sort of attractions and little connections here, they disappear. They go away. And that means this water molecule wants to go this way, and this one will want to go this way. And that will give us our liquid. Now let's say if we further continue to heat it up, we add more and more energy to our water. What will happen then is that they will grow so restless that they'll just want to burst away from each other entirely. And by doing that, we will then go from liquid water to steam. These water molecules here will be so restless, they will have so much energy in the form of movement that they will repel each other away in every single direction possible. And that is how we then have gas. Now, the opposite occurs when we cool something down. So let's say if we get boiling hot water. So we have our cup of water that is releasing a heap of steam. So we have a heap of steam coming out, and we pop it in the fridge. So by putting it in the fridge, it's a lot colder. The energy is going down. This is like giving a child a sleeping tablet. So suddenly the child will want to sort of slow down, not move around as much. They don't mind being close to each other, which means that our steam turns to water. Then, as we further continue to remove this energy, what will happen is that they will start to move so slowly that our little bonds over here, our little bonds will start to connect again, and it will form a lattice structure, and that's when it will turn to ice. Okay, let's move on now to classifying matter. So we have our matter here. The first thing we need to discuss is whether it is a pure substance or a mixture of two or more substances. So if we have our particular object, let's say for example our glass of water. Is it a pure substance? Do we have water, only water, and nothing but water? So let's say yes. So we have our glass of water. So we go down and it is a pure substance. So it means that it is a homogeneous composition. So homo meaning one or single. Now we ask ourselves, is this an element or a compound? Now I'm going to cover this more in depth in a moment. So an element is essentially something that cannot be broken down further by physical or chemical means. And you will see this on your periodic table. So a periodic table is the total list of all elements. So by looking here at our glass of water, so we think what is water? So it is H2O. So is it an element? The answer is no, it's not. Because if we look at the composition of water, H2O, it contains hydrogen and oxygen. So these are two different elements. So it means our glass of water is a compound. Now let's choose something slightly different from water. Let's choose something a little bit more delicious. Let's look at our jelly donut down here. So we've got our jelly donut. So our jelly donut, is it a pure substance or is it a mixture of the two? It is a mixture because if you think about the composition of a donut, it has more than one thing in there. Okay, you've got the donut and you've got the jelly. Now, as we move down here, so we go, yes, it's a mixture. We go, is this a homogeneous composition or is this a heterogeneous mixture? So how to distinguish between the two is if we have a look at our jelly donut and we take a bite from the end, we take a bite in the middle, and we take a bite in the other end. So if we take a bite from one end, we would get primarily sort of the donut portion. Now, if we took another bite in the center, we would have primarily jelly, because the jelly would be in the center of the donut. And then if we took a bite at the very other end, it would be mainly donut again. So because of that, it's not consistent all the way through. It's different. So if you were to take a sample from the end, the middle, and the other end, you would get 3 different compositions. And that is why the jelly donut would be a heterogeneous mixture. But then hang on a second, you may be saying, well, what is a homogeneous composition? So let's think of our delicious cup of coffee. So our glass of coffee has multiple things in there. We have water, we have milk, we have sugar, and we have, of course, coffee. But the thing is that if we had our glass of coffee, here, and I took a teaspoon from the top, a teaspoon from the middle, and a teaspoon from the bottom, at each section I would have coffee, coffee, coffee. Because it is consistent throughout the entire cup. So because of that, because no matter where I take a sample from, it's going to be the same, this makes it a homogeneous composition.